this type of question always just absolutely cracks me up because it's so simple and it's just a massive pain, and I don't really know why I signed up to explain this one, but let's do it. So, right, let's assume one solution. So the solution that to be assumed to be separable is going to be uxt equals x t t. So obviously that's t differentiated once, k squared, and then x differentiated twice. That's what the dashes mean. So we're going to compute partial derivatives of this. So we're going to do, let's say, u dash x. We're going to differentiate for x of this. So partial derivatives, if you aren't familiar and you're doing this, I have no idea what you're doing watching this video, but I do have an amazing video on how to find out partial derivatives. Watch that video. You basically need to know it for everything in maths. That's going to be x t t. So then we're going to differentiate in terms of x again, because we want to try and get this. And so you're going to get x dash dash x t t, because obviously we're not differentiating the t parts, we're holding them constant. But now we're going to differentiate for t. So you're going to get x t dash t. Cool. Let's divide. Let's first sub this all into here. So if we sub this now all in, we've got this differentiated once for t. So you're going to get x t t equals k squared, and then let's sub in for that beautiful. You're going to get x t t. So if we now divide both sides by, let's say, x t t, not the differentiated version, you're going to now get, so if I divide by x t t on both sides, x t t, this cancels out, and I think this cancels out. So we are left with t over, I'm now going to actually, I'm going to move this k squared down, k squared t t, which equals x dash x over x. I'm going to make this equal to some constant. So we're going to make it equal to negative lambda. But this is now the important part. You're probably thinking, why? Is this just random? Why have you done this? But solving this type of partial differential equation by separating variables is rooted in getting physical, meaningful, and mathematically useful solutions, particularly non-trivial bounded solutions that reflect the behavior of physical systems like heat, vibration, stuff that happens in the world. So when lambda is equal to or greater than 0, it gives us this oscillating trig solutions, which are typical eigenfunctions we expect in problems with, like, the Newman, or I can never pronounce it, Dirichlet boundary conditions. So for that reason, you make it equal to minus lambda. Making this just a little naughty lambda does change your end solution quite a bit. But anyway, we're not even halfway there. So let's crack on. Okay, this is called a Stern-Liouville problem, or Strom-Liouville problem. I can never pronounce any of these words, Thank God I do maths with Newman boundary conditions. So we know that these are all equal to each other, so we can start playing around. So you've got x differentiated twice, x plus lambda, which equals 0, and x dash dash 0, which equals 0, and we have x1, which equals 0. These are taken from the boundary conditions that we were given at the start. Let's now build off of that. Let's let our constant equal 0. So let's let lambda equal 0. So if we have x differentiated twice equals 0, then we're going to use a bunch of trivial solutions. So that means x1 is going to equal ax, and x is going to equal ax plus b. So these are trivial solutions. Let's let lambda equal mu squared, which is greater than 0. So when you let lambda equal mu squared, we can then plug this now in. We'll tie this up in a minute. I know. It kind of feels like we've gone on a bit of a tangent, but we haven't. So x dash dash minus mu squared x equals 0. So the trivial solutions are x equals a cos mu x plus b sine mu x. X differentiated one, so what we're going to do is differentiate this. It's going to be minus a mu sine mu x plus b mu cos mu x. And then we've got our boundary conditions. So let's apply them. So let's say we apply them here. We've got x when it's 0 is going to be b mu, which equals 0, therefore b equals 0. So I've just basically slapped that in here to this second part. And then let's do it when x dash 1, because remember, they gave it up here, so it's going to be minus a sine mu, which equals 0. So for non-trivial, a cannot equal 0. So we require sine mu to equal 0. And so mu would equal n pi, where n can be 0, 1, 2, and so on. Thus, lambda n equals n pi all squared. And actually, I don't know why I even put that there. And xn, x equals cos n pi x. We're going to tie this all together. We're going to tie it all together now. Because we've now done the x side using these general formulas. So we've used these two general formulas. We've substituted in the boundary conditions. We have some sort of solutions, but we haven't done the t side one. So now we're going to switch to the t side and use this bit. Okay, so the next step down the rabbit hole is we've got this xn x equals cos n pi x, which is the kind of generalized side of it. We can start plugging it in. So we want to solve the temporal ordinary differential equation, because we've had the x side, we haven't had the t side. So the temporal ODE is t dash t plus k squared lambda big T little t equals 0. General formula that up, which is going to be a n e to the minus k squared lambda n t. And so that's going to then be a n e to the minus k squared brackets n pi all squared t. So I've used the general formula, something that you need to know. Again, a lot of this question is about just basically remember general formulas and slapping it in. Because again, the next step is we have the general solution is the sum of all the eigenfunctions that we've created. Because we've created this negative lambda constant. So we want to summate all of them together, which is going to be uxt, which is here n equals 0 to infinity, and you're going to get an cos n pi x, obviously, e to the minus k squared n pi squared t. But n equals 0, lambda 0 equals 0, x 0, x equals 1. I'm using the boundary conditions. T naught t equals a naught, which is a constant in time. So for n that's equal to or greater than 1, the exponential decays over time. So the coefficients of an are determined by the initial boundary conditions that were set out. So we had ux naught equals fx. So therefore, we're going to use the Fourier cosine series. That's what all of this is. The Fourier series and the sine series of the cosine series. So you're going to get fx equals the summation of n equals 0 to infinity an cos n pi x. And I think we're kind of done. You know, you just kind of get lost in this kind of a question. But I wish I could say that was fun. It wasn't. It was horribly unenjoyable.